So today I thought I'd talk about this exponential growth question that comes from a deleted account. If you do much online chatting these days, someone will eventually talk to you about doing something with your money. Then after a while they disappear, either banned or to talk to more people as a different persona, or some combination of the two. In this case, the person wants me to invest with the company they have a referral code for, and they answer remarkably few questions, trying to keep you focused on quick, large returns. They won't say how the company plans on making the money in such a short period of time, or any tax measures that you need to know about because of it. They won't even answer relatively straightforward questions like which of the four packages they offer gives the best returns. Usually you want to reward people who give you more a bit than those who only come in with a little. And as a math nerd, I could see that this breaks that trend. They offer 15% after 8 hours, 25% after 15 hours, 55% after 25 hours, and 110% after 50 hours. I've been assured that those aren't annualized rates. After 8 hours, you would supposedly get your money back plus 15% on top of that, or 1.15 times your money, assuming that they give you anything at all, that is. When I first started exploring math as a kid, my first approach was to find the 15% first, and then add that to the original. It took a while before I figured out that I could just combine that into 115% or 1.15. So after one round, your gains kind of look like this, and we have the quick one going for 8 hours, and the long one went for 50 hours. In 50 hours, you could run basic 6 times with 2 hours left over. You could repeat standard 3 times or gold twice. So this is hardly a fair comparison, and we can try to make it a little more fair. So if you were to repeat the basic package 6 times, it wouldn't just be 6 times the 15%. You can reinvest what you've gained. $100 earns you 15. Add that to the original, and you're investing $115 and getting back 15% on top of the original 100%. So 1.15 times that, or $132.25. And after 6 rounds, it winds up being 231.31. So earlier we figured out that it was possible to repeat the standard option 3 times in 50 hours. So we can do a similar calculation, and the 25-hour smart option can be repeated twice in 50 hours, and we conveniently have no extra hours left over with that one. And this is a better comparison, but it isn't great since the basic option has 2 extra hours and the standard one has the most at 5 extra hours. And the gold package doesn't look so golden anymore, as the smart one looks particularly smart, giving you a bit more than the rest of them. If you were to look at longer periods of time, though, with the extra 2 hours from the basic package and the extra 5 hours on standard, let one of those catch up. There's a couple different ways to answer this question. The obvious one is to find out how many hours we need to go for so that all of the options end at the same time, and we have none of them with any hours left over. And this is where the idea of common multiples comes in. Multiples are something that you get when one number is multiplied by another number. A quick example of this would be if days consisting of 24 hours. So the number of hours you'll have in a number of days will always be a multiple of 24. So we're going to look through the multiples of 8, 15, and 25 and find one that they all have in common. 50 would be nice, but it's kind of optional since we already established that it wasn't a great option. But it also kind of automatically comes with the rest of them. If we don't care about optimization, we can just multiply our numbers together. 8 times 15 times 25 gives us a number that we can conveniently divide by 8, or 15, or 25 without getting any remainders. This gives us 3000. We can run basic 375 times, standard 200 times, and smart 120 times. And we can also do 60 cycles of gold. Another thing that we should take note of is that all of these numbers end in a 5 or a 0. That means we're doing 5 times as many cycles as we need to, at the very least. To sort of optimize things a bit, we can look for the lowest common multiple, which is the smallest number that can be divided by 8, 15, and 25 without any remainders. And to do that, we need to start by breaking down each number into its prime factors. I'm going to assume that there's already some familiarity with the prime factors and under-explain the idea here. Factors are things that you can multiply together to produce a given number. And a prime number is a whole number that can only be divided by 1 and itself without any remainders. An example of one of these is number 5. Some numbers are both prime numbers and factors of a number, and prime factorization is breaking a number down into a group of prime numbers that you can multiply together to get a certain number as a result. The numbers we care about here are 8, 15, and 25, and to a lesser extent 50. They break down to 2 times 2 times 2, 3 times 5, 5 times 5, and 2 times 5 times 5. So now that we have that, we can build a new common factor, this time using prime factors. Starting with the 8, we need 2 times 2 times 2. Next, we need to include the 15. We don't have a 3 or a 5 in there yet, so we'll put those in. Then comes 25. For that, we already have one 5 in our list, so we only need to add one more in to ensure that the result will be divisible by 25. And now we come to the 50, which consists of 2 times 5 times 5. All the parts are already in the mix, so we don't need to do anything. And that's why I said we didn't need to worry about it and it was going to come along automatically. So once we multiply all of them together, we get 600 hours, during which we can run basic 75 times, and 40 rounds of standard, 24 rounds of smart, and 12 rounds of gold. This is still 75 plus 40 plus 24 plus 12 were 151 calculations, so I'm going to resort to another shortcut, the exponent. And I'll under-explain this one quite a bit as well, since, well, I've done 3 videos in a row with exponents in them now. Exponents are a quick shortcut to repeated multiplications for basic, which gets you 15% each time, or ending with 115% of what you started with. You'll want to be multiplying 1 by 1.15, a total of 75 times. So we can jot that down as 1.15 to the power of 75. Standard is going to be 1.25 to the power of 40. Smart is 1.55 to the power of 24. And gold is 2.1 to the power of 12. So this doesn't actually reduce the number of calculations we need to do. It just gives us an easier way of writing it, and a way that we can quickly enter it into a calculator. You just need an exponent button on it, like any scientific calculator. If you set your Windows calculator to scientific, or if you type it into Google, or put it in a spreadsheet, or shout it to your voice assistant of choice, and then maybe shout at me for going to the trouble of finding the lowest common multiple when it doesn't really take much extra work to put a slightly larger number into a calculator. And now we can see they largely split off into 2 different groups that are pretty close to each other, but the 2 groups themselves are pretty far apart. Clearly, basic and smart are the better options compared to standard and gold, which we could kind of see earlier. Between basic and smart, smart is the slightly better option, and gold is the slightly worse one. So this approach has some limitations. It's pretty straightforward, though, and doesn't involve too many math concepts. But what if other options are added, or there are a lot of different durations to take into account? You're going to need to keep changing the number of cycles you calculate for each option so that you can do a fair comparison. So if we break out the heavier math concepts, we can look at these as a group of functions that relate hours to returns and graph them. There's something called the domain and range of a function, which is a math way of saying the valid input values and output values. As they're presented, the functions only have valid values at those specific points, which is what's been making comparing them difficult. Finding a part of the domain that's valid for all the functions we'd like to compare is one approach. We can also make this a lot easier by changing the function so that the domain includes all real numbers. They might not be valid options in the actual thing that person wants to promote, but they will give us a valid comparison. Instead of discrete cycles, we can just rewrite those in terms of hours. Having a different base and exponent also makes them a bit difficult to compare, but well, whether or not I can explain it, the rules of exponents allow me to change them to this. And this time, let's do the math first and explain later. We're already at a point where we can just put stuff in a calculator and get some fun numbers out. They're really long numbers, and we can easily see which one's bigger, as well as how there's a group of around 1.0176 and one group that's around 1.0149. Well, I'm in a mood to just sort of rush through this, so let's go back to what I said earlier about exponents being repeated multiplications. I hope we're fairly comfortable with this so far. One of the things we can do is multiply and divide, and that results in adding and subtracting exponents. And if we're comfortable with that, we can get a bit more abstract with stuff like this, where if you take 4 to the power of 1.5 and multiply it by 4 to the power of 2.5, you'd add the exponents and get 4 to the power of 4. You can then expand that out to 4 times 4 to the power of 1/2, multiplied by 4 squared times 4 to the power of 1/2. And if you separate the two 4 to the power of 1/2 values, multiplying them together gets you 4, or 2 times 2. If you have most other numbers and need fractional exponents like 1 over 8, or 1 over 15, 1 over 25, or 1 over 50, you're going to wind up with some pretty interesting numbers, which you'll need to find with a calculator. Now to generate more clutter, something to the power of 3 is something times something times something. If that something happens to be, let's say, n to the power of 4, we'll get this. And just for fun, let's suppose n is 9 to the power of 5. Now we're looking at 9 to the power of 60. And 9 is equal to 3 times 3, or 3 to the power of 2, but I suppose I should draw a line and stop somewhere. So we got here from 9 to the power of 5 to the power of 4 to the power of 3. Another way to get here is 9 to the power of 12 to the power of 5, or 9 to the power of 4 to the power of 15. How they're grouped isn't that important, which is why it's possible to separate the parts of the exponent in the question earlier, so that we get all the exponents the same, and then we can compare the base. And I should really come up with something to say to end these videos.